You're on, Dave. You're on.
Okay. As best we can. Let's do physics.
And try to rejoice.
I found my tolerance for other people today much less than it has been. So I apologize now if I snap.
Frankly, same.
All right. So we left off, we were talking about moment of inertia, talking about how it deals with distribution of mass. Let's work through a math problem and then we'll get to torque and then we'll combine the two things.
Is that S-state or solid?
Solid. So how fast is this mass, how fast is this going to, is the sphere going to be going when it gets to the bottom of the ramp? Assume that there is friction. And that it's not going to slide at all. So it's a perfect roll.
Good morning.
Is it?
Ish. If static friction is greater than 0, wouldn't it be kinetic friction then?
No, I'm saying it's not frictionless.
Okay.
All right, because we have this perfect roll here, and there's no sliding whatsoever, that kinetic is not involved.
Oh.
So the friction is going into getting this object to rotate. So let's look at it from an energy point of view. Let's look at the forces acting on it. What are the forces acting on the ball?
Friction. Gravity, or weight in this case.
Normal.
Of these three forces, which ones are conservative?
Weight, gravitational force.
Isn't everything except normal?
No, because friction is non-conservative, I believe.
It is,
I really
not
need to write
conservative.
I didn't-
Yeah, weight's the only conservative force here. So I have this thing rolling down the ramp, but I've got two non-conservative forces. So let's deal with that. I know that the work done is equal to the force times the displacement. If we think about the point where the friction is acting, which way is that point going to move when it starts to roll?
This way. Oh, wait. So, I don't know how to do this.
So I'm talking about that point on the ball.
It's, I don't know. Like
Wait,
this.
which way is the point gonna go?
Yeah,
Up.
up the ramp. So when I start this thing to roll, this spot is going to move that way.
Yeah. Well, are we supposed to use the right
The
hand?
spot or the ball?
No, just the spot.
Oh, okay.
The spot. So let's take that spot right there.
Okay.
And it's rolling down.
And
Assuming.
I'm just gonna go that way. I don't know how well you can see the dot over there.
I mean, we can see it pretty well.
All right. Yeah, good Erica. All right, so as it moves, think about which direction that spot is moving. Which way did it go? Wow, we were seeing something different.
Up?
That spot right there. So as it moves, put a little mark. Let me put the pencil right there so that we can see where it starts. It slid this though. Did it go through that side of the pencil?
No, it went
So it didn't go that way.
this way.
It's
And
going
the-
this way. I was looking at the edge of the ball, of the roll thing, so.
That edge right there.
In theory, in space, it would go that way.
Well,
It's also going clockwise, which is what I was thinking.
all right. Let's not talk in terms of clockwise right now. All right, so it's right there. As it moves, I mean, there is some movement in that direction, but there's also movement, yeah, that way. So in the immediately, while that friction is acting on it, it moves that way. So it is gonna be moving like that over a period of time, but in that at that moment right there, when friction is acting on it, it moves that way. And then it'll start to curve. In other words, the friction force is perpendicular to that spot where the friction is acting. Therefore, the friction doesn't do any work. So the work done by friction is zero because the friction force is perpendicular to the displacement at that moment. Now, how about the normal force of that spot? Well, we just established that it's moving in the direction of the normal force.
Right.
However, as soon as it lifts off the table, that normal force isn't acting there anymore. So the work done by the normal force is equal to zero because the normal force is practically zero. Well, actually, it depends on how you want to look at it. The normal force actually acts on it because delta x is approximately zero. Or you could look at it from the point of view as the normal force drops to zero very quickly. Because as soon as it lifts off the table, normal force isn't acting on that spot anymore. So the only force doing any work is the force due to gravity. Therefore, energy is conserved.
Delta X sub Y, right? When you say delta X is approximately equal to zero.
It's not of that point.
Oh, okay.
Point P. Somewhere there's another one of these pens around here. All right, so energy is conserved. E initial equals E final. I have two types. Well, what are the two types?
Kinetic and potential.
Because we have this object that is moving down the ramp and spinning at the same time, we have to deal with both kinetic energies. So I have K initial translational plus K, or linear, whichever way you like it, K initial rotational plus potential energy.
What exactly are we finding right now?
What is T?
Before we get too far, what are we finding right now?
How fast it's going at the bottom of the ramp. Yes.
What's the subscript for that first KI?
I called it translational, so I did a subscript T, but then I thought you could also call it linear, so like,
Thank you.
so whichever one you want. Now some formulas. What's the formula for translational kinetic energy?
For translational kinetic energy, 1/2 mv squared.
Yep, that's the one.
There's only translational in this case, though. Well, hold on,
It is
I'm a
wrong.
dumbass. Sorry. That caught me out.
MV initial squared plus formula for rotational kinetic energy
1/2.
I omega?
Yeah.
Squared?
Omega squared.
plus the gravitational potential energy.
Gravitational potential.
That
It's
when we're assuming that little g is relatively constant.
inertia. Oh wait, sorry.
It's just
Oh, MGH. Sorry.
Oh, which be a subscript I there. MGH initial equals the same stuff with final 1/2 m the final squared plus 1/2 I omega final squared plus MGH final. All right,
On the third tier, if you will, where it says KI something or other, what's that something or other?
where you okay
The subscript?
that there?
Yeah.
It's a T or an L, whichever one you want to use.
Oh, okay.
For translation,
and this board, what does the W mean?
Work.
So,
The work by the normal force is 0. The work by the friction is 0. Setting up a case for the fact that energy is conserved. All right. What is equal to 0?
Initial velocity.
Sure. That was the intent. I don't know if I actually stated it or not.
And because I say that the starting point is at the horizontal, then that means MGH final is also equal to 0.
Why?
Because the starting point is at final height,
Okay.
the origin. Origin point, starting point, same thing. Because no,
0 because, and that's 0 starts at rest. So we simplified it down to, I start out with all this potential energy, no kinetic energy, and then as it goes down, that potential energy gets converted into kinetic energy. Any questions at this point?
Can you just wait for a moment, please?
Yesterday when you talked about like how 1/2 MV squared and 1/2 I omega squared, did you like, when we were talking about it, you were like, oh, the MV squared one works no matter what, like they're always equal to each other? Is that the same thing for like, for example, on the other side of the tier, where it's like final velocity and omega final squared, whatever, but those two equal each other? Like those two term variables, are they equal?
No, those two terms are not equal to each other.
Okay, just wondering.
Can you remind me again why the first two are 0? Because velocity is 0? Is that it?
Yeah, because it starts out at rest, it's not moving, therefore the linear speed is 0 and the angular speed is 0. So we have this potential energy at the beginning. There's no common term, or common factor to each term, so there's nothing to cancel out. So we now need to do a little substitution, because we do have a formula for moment of inertia, and we have a formula for omega. MGH initial equals 1/2 MV final squared plus 1/2. What is the formula for the moment of inertia of a solid sphere?
2/5.
What, 2/5 entire mass overall radius squared?
So 2/5 mr squared, omega squared.
Do we have to say like the entire, like, can we just say MR instead of
Yeah.
capital M, capital R?
Sweet.
I mean, this is the mass of the whole, these are all masses of the entire object, so right now, we can cancel mass out.
Yes.
In a perfect roll here,
Mhm.
what is r times omega? Or r squared omega squared?
No, I don't wanna answer anymore.
What's r omega?
R omega? That's just V,
Yeah, so that's v
V squared.
squared. So I'm now left with g h initial is equal to 1/2 v final squared plus 1/5 v final squared, which is 0.7 v final squared. We're trying to solve for vf. So vf is equal to the square root of gh over 0.7,
Just 1/2 of 2/3.
which is the square root of 9.8 times centimeter height
Wait, where are we getting negative?
divided by 0.7.
Oh, wait, Dr. Fox, where are we getting -7 from?
-7,
Yeah.
what, here, that's a 0.7.
Oh, sorry. Oh, is that 1/2?
1/2 plus 1/5.
Got it, thank you. That was along with that. 7.
Wait.
So,
So we're around 12.
So, did we cross out the M?
Done.
Yes, we did, okay.
What
So
you
then
get,
it's
Erica?
just GA, GH.
11.83.
11.83. Thank you very much. All right, so we have how fast it's going.
Okay.
If it were just voxel and frictionless ramp, then the rotational term would disappear, and you'd be divided by 0.5 instead of 0.7.
Where did we get 0.7 V?
I have 1/2 vf squared plus 1/5 vf squared. That's 0.5 vf squared plus 0.2 vf squared, which is 0.7 vf squared.
Okay.
If you'd rather do fractions, get a common denominator, get 7/10. Okay. Questions?
No.
Stay. No. Let's put those back. So if I pull on this rope, I'm gonna deviate away from this for a bit, we will come back to it. If I pull on this rope to the right, to my right, which way is this gonna spin?
Oh,
All right, now would be it's gonna spin to the back of the room, or it's gonna spin, sorry, to the front of the room or the back of the room.
front of the room.
Front of the room, so it's gonna do a backspin.
Yes. I'm very confident.
I agree.
Anyone wanna disagree before we do it?
Watch it, Stacy. Watch it.
Back, you said to the back of the room?
Yeah, why not?
It's gonna stay still. I changed my mind.
Oh my god.
What the
Oh my
heck?
god.
No, Dr. Fox, you did it wrong.
You didn't pull it
I did it wrong.
Yeah.
If I yanked it really hard, it would give it.
Did it not spin because of kinetic or something?
Kinetic what?
Energy?
Well, it,
Like, in my mind, it should have spun.
oh, it stayed in place?
Yeah.
Yeah, that, if I had a frictionless surface, that would have been the case.
Oh,
but it's not a frictionless surface. So the question is, why? What is it that happened? Well, I applied torque. So let's talk about torque. Torque is the rotational analog of force. It's an influence that might cause angular acceleration. You know, it's incredibly specific like that. All right, so I've got a door right here. If you're not convinced, door, stay. Come on, stop, stop. All right, so what I want to do, it's really nice when it opens into the room. What I want to do is I want to open that door as efficiently as possible.
With AKA the most efficient force or what?
Most efficient torque. Because I'm going to get it to rotate, torque is an appropriate term. All right, so how do I open the door as efficiently as possible?
Like in terms of like least amount of energy,
At least effort on my part.
walk through it.
Walk through it.
Not through the door, but just walk and the door will move out of your
Bare
way.
Wow.
And then keep walking and you're out. Just face through.
That did not seem like it was a particularly efficient way of doing it.
Just walk towards it with
Scoot it out of the way with
and
your
like-
I
foot.
leaned forward too much.
Scoot it out of the way with your foot.
All right. That still doesn't seem like it's the most efficient way of doing it.
Yeah, you have to use the end.
I did use the end.
The other end of the door.
So if I push on the other end, then it'll look
And
more
not the
efficiently.
top end.
No, I'm not gonna do the top.
Good.
All right, so push on the other end, it'll open more efficiently.
The end with the handle, yes.
Okay.
Whoa, whoa, whoa.
Oh.
Is he doing
Alright.
the corner right
I'm
now?
pushing on the end.
Oh.
I'm taking it too serious.
Man, that worked less, worse than gravity.
Centripetally, you have to do it perpendicular to.
Just push on the door handle.
Perpendicular to it. Okay.
Perpendicular to. Yeah.
Wouldn't the door handle be like this and I could not let himself out? Never let him back in. In his car, in his car, I think.
That was not efficient either. I pushed perpendicular, actually I was pushing perpendicular to it on the end of the door too.
How is it not efficient?